Alright, vintage computer friends. Yeah, thanks for tuning in again, and today we have a look at another gem in my collection. It's the 1976 Science Fair Microcomputer Trainer that was released, by none other than the famous Radio Shack, a division of Tandy Corporation, USA, Fort Worth, Texas. And yeah, I'm very happy that I got this. This was new old stock actually. Still even see it, That's a wonderful box as well, and the trainer is really new out of the box, so it was in wonderful condition. And it was actually, as far as I know, the first micro computer trainer ever. So Radio Shack really did groundbreaking works there, and in some regard it shares a lot of similarities with the Busch Microtronic. Both are 4-bit TMS microcontrollers. In this case the machine is running on a TMS1100 4-bit microcontroller, whereas the Microtronic has the bigger brother of the TMS1600. Also the clock speed is a little bit reduced, so this is actually either a ceramic oscillator or a crystal, I'm not sure, but it's clocked at 400 kilohertz. And yeah, I mean, it looks a little bit like a toy, this is all cardboard here, but I mean, it does its job, and it's actually a real computer. So I'm going to have a number of videos about this wonderful Science Fair Microcomputer Trainer later on my channel. But for now we just want to see how it compares in terms of compute speed, right, with the Microtronic as well as the Cosmos CP1 that we already measured. And I don't know this machine very well yet, but I know it well enough by now that I know how to write a simple program, right? So basically you see the address bus here. It's a what is it actually? A 7-bit address bus, right? So the machine has 128 memory cells, and that can be used similar to the Cosmos CP1 for data as well as for programs. And so you can reset the machine. It's actually battery powered, right? In the back it has like 6 AA batteries, right? And then the voltage is available here, and you can set up your circuit. So you need to actually connect the microcontroller to the keyboard and to the LEDs and so on, but it's in a sense reconfigurable. But this is kind of the default configuration, this wiring that's required in order to make the machine run. So here you will see the opcode, right? So it's 4-bit opcodes, right? And then this is the address actually. So we can step through the program by resetting the machine. Then the address counter is set to 0, and then you can increment the address, right, and see it's displayed in binary there, and the program shows on the hex LED. And I keyed in a very simple program. So 8 means TIA, right, and it's transfer immediate into accumulator. So we are loading the accumulator with a value, and we are just loading it with 0. So I'm just writing a very short program here. And next it's F. F is an unconditional jump, and then you need to specify 2 nibbles 4-bit values for the target address. So we are jumping back to 0, 0. So it's just a very simple program that loads the accumulator with 0 and then loops. And why am I doing this? So I need at least 2 instructions basically, right? A program that uses 2 addresses, and this is like the shortest program I could find that runs in a loop, because we are simply going to observe basically with the oscilloscope the second address bit, right? And that way, we can actually see how fast this machine is executing these 2 instructions, and we get an idea. So in order to run the program, there are various run modes. There is single stepping, and you can also run the program normally, and for this you would use 2 and then run. But first we need to reset the machine again to set the monitor address or the program counter to 0. But you can also key in an an arbitrary address here using the buttons, right? For example, the highest address is 127.7f, and then you can do address set. You see that the address bits are all coming on, right? But for now, let's just run our program to run and see what we get. So we see that our address bit 2 basically is lighting up a bit, right? So, and what does the oscilloscope tell us? Alright, I zoomed in a little bit so that we can observe the oscilloscope a little bit better and what it shows us. So we see that the machine runs at 217 Hertz, right? And yeah, we are executing a program that takes 2 instructions, right, in order to reproduce this square wave. So I would claim that we multiply this by 2 and that the machine executes at 434 instructions per second. And using our newly introduced unit hips, hundreds of instructions per second, the machine runs at yeah, 4.3 hips, right, where the Microtronic was more in the 1.1, 1.2 hips region. So this machine is about, well, yeah, factor of 3.8 faster than the Microtronic. So yeah, great job there, Radio Shack. That's kind of surprising, given that the microcontroller is running at a even lower speed here, right? So this is only 400 kilohertz instead of 500 kilohertz in the Microtronic, and the microcontroller is of course a smaller version, the TMS1100 instead of the 1600 microcontroller, right? But you might be surprised, you know, if this is the address bus being observed while the program is running, and our program had instructions from address 00 to 04 actually, right? Why are we only seeing bit number 2 toggled while the program executes, right? I mean, obviously all of the memory from 00 to 04 needs to be accessed in order to execute the program, right? And this is not just because it flickers so fast, so we can see it, but if we put the oscilloscope on bit 1 on the address bus, it's really a flat line, right? And so confirming our visual suspicion, and also the third bit, you know, is also a flat line. So it's really the only activity that we see here while executing the program on the address bus is at bit 2, right? And why is that? Well, if we look at the program, then those are the addresses corresponding to the opcodes, right? So we have the opcode 8 TIA load accumulator, right, with value at address 0. So this address would show up while running the program on the address bus. And then the next address is the operand, right, at address 1. But the operands, you know, don't seem to show up while running the program on the address bus, right? So because otherwise we would have seen flickering of bit 1. And the same holds true now for the jump instruction F, right? So at address 2, this is actually what we were seeing. The 1, right, on the second address bit corresponding to the jump instruction. And its operands, target address 00 and address 3 and 4 are also not showing up, right? And then of course the program is already back at 0 now. So this is how they implemented that. And yeah, so great job. Also here are all the opcodes listed, right? And so you see it's only like 16 opcodes. So one level opcode, and then some of these opcodes take 0 and some take 1 or 2 operands. Yeah, a very interesting machine, and it's actually a real computer. So it also has some ROM programs built in. So as I said, I want to do a deep dive video about the microcomputer trainer, Science Fair Microcomputer Trainer at some point, but for now I'm just going to show you one of the ROM demo programs. If we hit 9 run, then it turns into an electronic organ, right? And I think our program is still in RAM, so I can still execute it using 2 run. Yeah, still there. And then there are other fun little games, for example a musical guessing game, and this is at B run. So let's try this one, B run, and it always starts with Do, so it's basically a Simon Says, and I already lost, you know. Let's try it again. Got that right. Okay, well, I don't get very far there, but I mean, it's kind of really an intriguing machine, and I'm looking forward to learning more about it and its programming model and sharing this with you on my channel. So stay tuned for future videos. Until then, thanks for watching, take care, bye.